So this is the second video, and here we're going to talk about what happens, why chemical reactions happen. The explanation we have is the collision theory, and you can see here in the drawings it's about collisions. As it says, reactions occur when two or more molecules interact and molecules change. What happens is that, for example, we have this oxygen molecule, the red one here, and we have two hydrogen molecules, and they are going to bump into each other. Okay, they are going to collision, and in this collision, the energy released is going to break these bonds. It's going to break these molecules in the middle, and they are going to form new bonds. Like, for example, they are going to, again, this molecule, this hydrogen molecule is going to break, but they're going to stick together as this hydrogen-oxygen molecule, and that is water. So what collision theory says is that molecules collide, and in this collision, when they bump into each other, they release energy, and that's the energy used to break the bonds, los enlaces, that tie the molecules together and create new ones, okay? New bonds. Here we have two new bonds, hydrogen-oxygen and oxygen-hydrogen. So, as a summary, the collision theory states that molecules must collide in order for reactions to occur. Here again, we have two other molecules, and they collide here, and they break the old bonds here, and they create new ones, because they are going to stick now, these two ones and these two ones, and make new molecules. So it can happen in very different ways. But for a collision to happen, collisions happen all the time, but successful collisions must have the correct orientation, because, for example, we have seen here that they collide in this exact position. That's how they stick together this way. But if they are not perfectly oriented, like this or like this, these are not perfect orientations, because they are not going to form a new molecule, because they are interacting in a bad way. And also they have to collide with enough energy to break the bonds. If they come and they are very slow, nothing is going to break. So they have to have a lot of energy. They have to move faster than the normal way. And so again, for this to happen, we need to have two factors. The molecules need to have the right energy. That is, they have to move enough rapidly, and also they have to have the right orientation, like these ones, not like these ones, for example, because here they're going to collide, but they are going to bounce back and nothing is going to happen. So if these two factors happen, then we are going to have products. But of course, you can imagine to have these two statements, or these two factors again, so that they happen at the same time, is not so common. So not all the collisions are going to produce products. Only a small percentage of molecules have both correct orientation and enough activation energy. Because, otherwise, all of the reactions would occur almost immediately, and it does not happen. They are slow, sometimes very slow, some other times, because, again, you need to have these two things happening at the same time. Again, if the reactants are moving too slowly, Okay, they are approaching each other, but they are too slow. They are going to bounce and nothing is going to happen because they don't have enough energy to break the bonds. If they are not facing the right way, again, they are going to bounce and nothing is going to occur. So we need to have, again, enough energy. The reactants have to be energetic and they have to be correctly oriented. And then, only then, when these two things are achieved, only in this case we're going to have the chemical reaction happening, and we're going to have products. Otherwise, we have the same reactants that we had before, only moving in a different direction. And what are the factors that can affect the speed of a chemical reaction? Well, first, there's more than the ones that we are going to see here, but let's just see at least four. The concentration of chemical reactants. Of course, you know this because you have tried when you are, for example, cleaning something. What you're doing with the soap or the detergent is to create a chemical reaction to dissolve the dirt, and you know that if you put more, it's easier. So concentration matters. Okay, if you put more, the chemical reaction will be faster. Again, why? Because when you put more, there are more collisions happening, and so more things happen. So the chemical reaction speeds up because you can see more collisions in the end. I mean, it's not the same to see one that to see 100 collisions. And the more reactant molecules that they are colliding, the faster the reaction will be. Here is the opposite. Why do we seal our food? Because air is continuously, it has a lot of things and a lot of bacteria and so on, and these bacteria are going to produce chemical reactions, and if we don't make these bacteria touch the food, of course there are some bacteria that are going to be inside anyway, but if we have all of the bacteria touching our food, the reactions are going to speed up, and that's why our food is going to last less. So again, we protect our food to have less contact with possible bacteria that are going to create the bad chemical reactions. Another factor we have is temperature. We know also that if we increase the temperature, because we have studied, temperature is a measurement of the speed of the molecule. So the more temperature, the more energy they have, and the faster they move, and everything happens faster, and so on. So if we increase the temperature, normally we will have more collisions, and then the reaction will be faster. And for example, when we want to cook, if we put the heater at the maximum, everything is going to happen faster. And the opposite, if we freeze our food, the rotting reactions that spoil our food are going to happen much slower. And so if we increase the temperature, the reactions are going to happen faster, and if we decrease the temperature, the reactions are going to happen slower. But why? Again, because when we increase the temperature, the particles move faster, or the molecules, now that we know what a molecule is, move faster, and then there are more collisions, and more collisions means more reactions. I mean more in this picture, more collisions is like more products in the end, so the chemical reaction occurs. Another factor is catalysts. Catalysts are a special substance, a kind of substance that increase the reaction rate without being changed at the end of the reaction. That means that they are not changing their structure, they are not combining with anything or at all. There are things that speed up the reaction, like they help the reaction to occur, but you can get them back like unchanged at the very end of the reaction. And for example, enzymes, these are the main natural catalysts, and we use them to create beer, or also in soap and detergent and so on, because they speed up our reactions. And that's the meaning of it. I mean, you need to memorize this, because it's like it's nothing that you really see every day, because you think the beer happens naturally, and you don't know that if you don't put the catalyst is much lower. And like these are common day examples, but the catalyst is something you need to memorize. And finally, the particle size of chemical reactants. You know this because, of course, you have seen someone cooking, or I hope you have cooked sometime in your lives. And the more surface area on which collisions can occur, the faster the reaction. And here it's a bit weird, the sentence, because you think this has more surface area than minced meat, but it's not true, because here you can only, the contact surface area is only the one that is surrounding the chicken. But if we cut it, then we have the top and the bottom of this piece, and then the other piece who was inside. If you cut it in small pieces, it's going to have also it's going to be touched by air in everywhere. So here, imagine this was like a piece of meat, beef, whatever, but now it's in such smaller pieces that every piece can feel, for example, a frying pan, and everything that was in the middle is now spread, and everything can become in contact with oil and temperature and so on. By the way, what is happening when we cook something is we change the proteins inside, for example with eggs or with meat and so on. That's why it changes the color, and it changes the flavor. As we saw, those are indications of chemical reactions. So if you have cooked chicken, it takes like 2 hours to do it in the oven. But if you do mincemeat in a frying pan, it's like, I don't know, maybe 20 minutes, so it's much faster. And that is because every piece has the surface, and if you add up all the surface of every piece, the surface area of all the pieces together is much greater than the surface area here. I hope you understand this. I know it's a bit difficult, but we will do a session for doubts, and I'm sure this will come out, because I think this is the hardest part. Well, chemical equations. We have seen some of these. And chemical equations are the way we have to express a chemical reaction. For that, we need to know the chemical formulae of the reactants and products. This you don't need to know it for a second of ESO, but we're going to study some important formulas to know. In this example, for example, we have sulfur, and we have iron, and we have here a compound, okay? And this is a different substance than these two. separate ones. Again, this is a chemical reaction. We express it like this. Here, before the arrow, this is an arrow. I don't have the arrow symbol, so I put this, but imagine this is a perfect arrow, okay? And before the arrow we have the reactants, and after the arrow we have the products. It can be 1, or it can be 2, it can be 3. Here in my examples I just put 1, but that's just a coincidence. It's not meant to be only 1. And so that's the thing. The arrow means the direction of the reaction. So it means that we're going to transform these two substances into a new one. And if we need to add different substances, we add them with a plus. In some formulae, we have some equations. We have numbers before the substances. So here we have oxygen. You know, oxygen has 2, and this number means the number of atoms we have in these molecules. That is 2 atoms of oxygen. But we have another number here. This is a stoichiometric coefficient, and it means the number of molecules we have. So this is the number of atoms inside the molecule, and this is the number of molecules that is transforming in the reaction. Here we have then 4 atoms of iron are combined with 3 molecules of oxygen, and here we have 2 molecules of iron oxide. To work a bit with these chemical equations, you need to know this important formulae, okay? I'm going to ask this in the exam because these are very usual ones, and of course I think you know water with 2 hydrogens and 1 oxygen, carbon dioxide, this is also very common, oxygen of course, hydrogen, yes. And this is important because it's very toxic, and it's the pollution we have from cars, and methane. This is very common too, and is the base of all the organic chemistry. Ammonia, this is the thing we use to clean, for example, ammoniaco, okay, so you need to know this one. This is the salt you use in food to eat, but it's it's made out of sodium and chlorine, and this is the acid you have in your stomach, and this is nitrogen, and is the main substance you have in air. In the air we breathe, 74% is nitrogen. So these are everyday substances, and we need to know them. I mean, this one, for example, is one of the, this one and this one are one of the main gases that are affecting us for the climate, the greenhouse effect. You know, the global warming and so on are produced by some gases in the atmosphere, and these are the main 2 ones. But we're going to see an exercise to see what I mean. This is the exercise, but I have it solved in the next slide, so I'm going to go and read it in the next one. It says, depending on the conditions, carbon and oxygen can react in 2 ways. A carbon atom combines with a molecule of oxygen to form a molecule of carbon dioxide. Or the other way, 2 carbon atoms react with a molecule of oxygen to form 2 molecules of carbon monoxide. First, identify the formula of these substances. Carbon atoms are represented in black and oxygen atoms are in red. So here, if I identify all the formulae here, I can see if carbon is black and oxygen is red, this is CO because it's just this, and this is 2 oxygens and 1 carbon, this is CO2, carbon dioxide, this is this one here. This is also toxic, I have to tell you. Oxygen, 2 atoms of oxygen, that's a molecule of oxygen, and 1 atom of carbon, this is carbon. And be wise, for every reaction above, identify which are the reactants and which are the products. And also I'm going to do two B and C together, explain with a drawing based in collisions theory how every reaction happens. So first part, B. A carbon atom combines with a molecule of oxygen to form, that means the arrow. So before forming are the reactants. So reactants are carbon atom and molecule, and carbon was number 4 and oxygen was number 3. To form, that means something is going to form, so that means the new substance is going to appear, and that is going to be the product. And the product is a molecule of carbon dioxide. And here we have products, then it's carbon dioxide, which is number 2. How can we represent it? So a carbon is going to collide with the oxygen and it's going to form the carbon dioxide. So these are the reactants and this is the product. And this is the arrow that we have, this arrow for chemical reactions. In the other chemical equation, 2 carbon atoms react with a molecule of oxygen to form 2 molecules of carbon monoxide. So, again, when we see to form, before to form is reactants, so carbon, number 4, and oxygen, number 3, are the reactants, and products is only after to form we have carbon monoxide. So carbon monoxide, this is number 1. And the drawing could be like this. This is the main arrow, this is the arrow that means to form, okay? And before it we have 2 atoms of carbon colliding with 1 molecule of oxygen, and they're going to produce 2 molecules of carbon monoxide, okay? As you can see, we have the same atoms always before and after the main arrow, okay? And here, this is the end of the lesson for today, and this is the homework that is due for Wednesday.